everybody. Welcome to this week's Rough Cut. It's really a great, come on in. It's a great pleasure to have David Battisti here. As you know, he's also talking tomorrow night in the Western People and Lands series that the College of Letters and Science is offering, and his talk is at 6 tomorrow at the Museum of the Rockies. So please come to that. Dave is the Tamaki Endowed Chair of Atmospheric Sciences. He got his PhD at University of Washington and then was one of those lucky people that ended up working there for his career. And he's interested in climate variability and all the things that cause climate variability, from the oceans to the atmosphere to the land to sea ice. And he's also a real specialist, I think, in ENSO, the physics of ENSO, and how decadal and annual variability in the tropics then radiates out to the higher latitudes. And for me, Dave's one of my absolute favorite climatologists / paleoclimatologists. He's just a wonderful person to brainstorm with, and he's been involved on various projects that I've been involved in over the years, and it's just so great to have him here. So please welcome David.
Thanks, Kathy. Thanks everyone for coming. Thanks for having me here. It's been a blast already, and I kind of knew it was going to be, but it's even better than I thought it was going to be. Yeah, okay, so ask questions at any time because I can rearrange stuff. I don't have to get through all this. This is actually some work that mostly was led by one of my graduate students who just finished, Alyssa Atwood, and she said she was interested in looking at what's going on in these last millennial runs. It's a coordinated series of experiments that I'll talk about in a second. It was run by many of the major climate modeling groups in the world to see what happened over the last 1,000 years in climate. And she wanted to hire an undergraduate, this is this person, to help her just process all the data. I said, sure, fine. And she did. And then Dargan got involved. And then somehow at the end of this, even though Alyssa was my student, I wasn't involved early on, but then I got really heavily involved. And so we all ended up writing this paper that's in press, I think, in the Journal of Climate right now. So why was there a little ice age? What we're going to do is go through these runs that people did, these experiments, forcing their models with the observed forcings, and we'll talk about that in a second, and understand why the models did what they did, comparing what we would call a little ice age period to a MCA, like a medieval warming. There's another word for it. Help me out. Yeah, right. Good. Medieval climate anomaly. Thanks. For some reason I have trouble with that. Okay. So a few slides with overview of what the little ice age is from the paleoclimate data, description of these model experiments, and then the work that we did, which was to analyze the output of these to figure out what is the forcing and what are the feedbacks, why the models did what they did. And then a little bit talking about what the memory is. I'm going to skip this section for today. Okay, and I should not point to the screen, right? I should describe everything. Okay, just a few slides. What is a little ice age? Here's just a few placeholder for a lot of different records. This is a measure of the sea ice extent, top one here, in the North Atlantic. All these are from 800 AD to 2000 AD. And sea ice extent goes up from the medieval climate anomaly to the little ice age period, just general air cooling. If you look at the Iceland ice cap extent, this is measured from varves, the thickness of varve sediments at this lake in Iceland. You can see it increases as you go from 800 AD up till about 1900. The North Atlantic sea surface temperature reconstruction is a combination of delta 018, 4M assemblage, modern analog techniques, and magnesium calcium measurements that show that the North Atlantic is generally was warmer in the medieval climate anomaly and then cooled off. Greenland temperature, this is from delta argon 40 and delta N15, and just so it shows a very similar thing to the delta 018, cooler conditions in little ice age. And then here's northern hemisphere temperature reconstruction. There are better reconstructions than that now, but they all tell you the same thing, basically. Compared to this period of 800 to 1200 AD or so, this period following it from 1400 to about 1850 was quite a bit cooler, and particularly in and around North Atlantic, but also throughout the Northern Hemisphere. Okay? Not my data, so I'll just say that that's the consensus picture in the literature. Here's another picture. These are anomalies with respect to the mean from 1200 AD to 1970. And each one of these is kind of a normalized strip. So red means it was warmer, blue means it was colder, and each of these regions and areas are Arctic, Europe, Asia. And you can see there's a lot of inhomogeneity here. But in general, there's this period here from 1400 to 1850 where you see a lot of blues, right? And there's this period here between, say, 800 and 1000, you see a lot of reds and yellows, right? Kind of suggesting that it's not everywhere all at the same time cold and warm, but on average over these time periods, it's warmer here and it's colder here. Okay. All right. And the estimated cooling, if you look at the Northern Hemisphere average, is anywhere between 1/10 of a degree and 1/3 of a degree Celsius, global, Northern Hemisphere average. Okay, so these climate model simulations, every group was asked to run a simulation of the last 1,000 years with the observed forcing. Now, observed is also reconstructed, right, because there was no one making measurements of aerosol optical depth, for example, in 1000 AD. But so here's a reconstruction. The big forcing terms. Here's a reconstruction. The top panel is volcanic. It's the measure of the extinction of visible light you would get from the top of the atmosphere to the surface. So what doesn't reach the surface due to a volcanic eruption. And there's two different colors here. We'll come back to them. There's two different reconstructions. We'll come back to that. Here's the observed from bubbles and ice cores, methane, CO2, and nitrous oxide concentration, and they're kind of wobbling around. These are small changes. This is 275 ppm of CO2, right? And this is 280, so it's 5 ppm. These are really small changes, but they're changes, and there's less CO2 in this time period than there was in the medieval climate anomaly. Here's a measure of the changes in blue is Northern Hemisphere summer insolation. And you can see there's a pretty strong decreasing trend in insolation associated with the precessional cycle, where there's about 3 watts per meter squared less coming in 1800 than there was in 800 AD, right, in the Northern Hemisphere summer. And this is the Southern Hemisphere summer, which has no change because the changes are mostly in the transition seasons instead of winter and summer. On top of this, you see these little wiggles. What's plotted here is if you take the global average, annual average away from these records, you're just left with the sunspot cycle, basically. It's just this variability in the solar, the intensity of the sunlight. And what you see here is sunspot cycles, and then you see places where there is no sunspot cycle. So here's the Maunder minimum. This is a Spora minimum. I don't know if everyone knows the rest of these. I don't know the rest of them, but those are them. And so there's a little bit less energy coming from the sun at these time periods of low sunspot activity.
Can I ask where?
Yeah.
How you got that?
Well, I didn't get it, but you mean how they get it?
That's not from cosmogenic isotopes, is it?
It is. I'm pretty sure it is, yeah.
With the 11-year cycle on it?
Yeah, yeah. But I can give you the reference. I'm not going to try to defend it, but
I know you can get the envelope. Did they just superpose a 11-year period on the envelope?
Well, where'd they get the 11-year period, though? Because you can see there's huge variations in this 11-year period, right? I mean, and so maybe that's what they're doing. They're just scaling up the 11-year period with the envelope. But let me just get you the reference, okay? And you can see there's two different reconstructions here, the green one and the red one, so they don't, there's disagreements here. I'll just tell you it doesn't matter, okay? So it don't worry about it. I just gave away punchline. So sunspots is not the answer. I should have done that. Oh, dang. Because that's one you always read about, little ice ages about sunspots. It's not about sunspots. So there we go. I can sit down now. No, but there's other things going on. There's volcanoes. There's greenhouse gases. There's precessional cycle and sunspots. Okay. Okay. So here's another look at the volcanic reconstructions. There's two of them here. One of them is red, which is the Gao, and the other one is Crowley, which is in blue. And you can see they disagree. You know, like here, these guys have a volcano going off. They have basically 15 watts per meter squared less reaching the planet, you know, for a 2-year period. And these guys say, oh, sorry, it's 35, right? So there's really big disagreements in these data sets. They don't even agree, like these guys have a volcano going up here and the other one doesn't, right? So they even sometimes disagree on the timing. Where these come from is they come from the ice cores. One of them did the reconstruction based on using 53 ice cores from both hemispheres. The other one used less, I think 12 ice cores, mostly from the northern hemisphere. They differ in how they're going to distribute the aerosols as a function of latitude, which matters. You know, to some extent, we'll see how much it matters. And they also differ in how long the eruption is going to last, and also when and what time of year they're going to put it in the seasonal cycle, which you generally can't tell from the reconstructions. So do you make it a June volcano, or do you make it a January volcano? So there's differences here that are quite striking, and you'll see in the end they're important. Well, okay, we'll see. Oh, there's one I have to mention here, which is the fifth force. Climate extremes, recurrent crisis, and witch hunts. So I love this guy. I rode a train with this guy for like 3 hours one day, and he's just really interesting. He went through all these billets that they posted in the towns in like Switzerland, and they you know, tell the town what's going on, what activities going on in the 1500s and 1600s. Went through all of these, you know, libraries and museums and got these billets and was analyzing it for a number of times. They were mentioning witches and witch burnings and how many burnings were happening and what was going on. And he just correlated, and he showed that when the glaciers were advancing, there was more discussion of witches and witch activity. And the idea was the women are up in the fields doing the work in the summer, and the men are in the villages doing whatever they do. And there's like a lot of idle time, you know. Yeah, right. If you've ever herded animals, you know there's not a lot of idle time. But there were a lot of idle time, and they were up there, and they were practicing witchcraft, and that's why the glaciers were coming down. So it's time to burn witches, right? And sure enough, you burn enough witches, and the glaciers start to retreat. And so you see measuring this, showing that, yeah, as the glaciers advance, more and more witches burn, and then they retreat, they stop burning witches. So it works, you know. Anyway, that's an interesting story. Okay, so if you take these climate models, and I think we analyzed 8 of them, data from 8 of the models that use these forcings. Some of them use one volcanic reconstruction, some of them use another one. We'll talk about that. And what's shown in green here is just the solid green line is the average of what happened over all the climate models in a 1,000-year control run where there was no forcing imposed. You just let the model go, and the atmosphere interacts with the ocean and the sea ice. There's no volcanoes going off. There's no CO2 change, no nitrous oxide change. No change in the orbit of the sun, no sunspot cycles. And you can see there's variability here, right? And the green is kind of the spread, which gives you a measure of the natural variability of the climate models without any forcing. And the dark blue line is the average overall climate models with forcing, right? So you can see the models start like out here, and then they slowly get colder and colder and colder, and by the end of this 1,000-year period, they're about 0.2 of a degree colder than the control run without any forcing. And you can see these big spikes that are clearly related to the volcanoes, right? These big cold spikes here are related to very big volcanoes that are just putting a lot of aerosol in the air, blocking the sun, cooling the surface. Okay. So the models cool anywhere between 0.15 and 0.29 degrees C, which is, you know, in the ballpark of what the observations show you. This is northern hemisphere average temperature. And the reason why you do northern hemisphere average temperature is because there's not enough data in the southern hemisphere to tell you what the temperature is. Right? Okay. So we'll define 2 periods here, the medieval warm period from 950 AD to 1200 AD, and a little ice age period from 1600 to 1850. Just average the climate in each climate model of those 2 periods, take the difference, and we're going to say, why do they differ the way they do? Okay, so here's the difference each one of these pictures is for one of the climate models of what happened comparing the Little Ice Age period to the Medieval Warm period. So it's a difference. And what do you see? Here's the scale. Dark blue is minus 1.5 cooling, Little Ice Age minus medieval climate anomaly. And 1.5 red is warming. What do you see? Cooling, right? Here's the multi-model average. You get cooling. It's not uniform. It's more cooling in the high latitude northern hemisphere than it is anywhere else, although each model differs in the amount of cooling it gets, and even the pattern of cooling is different. Southern hemisphere in general is cooling. Here's the model where it warms. The GIS 121 model, it warms off of Antarctica. But in general, it cools, right? That's the structure. If you look at, so cooling occurs in all models. There's a large range of how much cooling is each model, about a factor of 2 difference between the models. And the spatial pattern is roughly similar, but there are notable differences. Okay, here's the same picture for sea ice. Only 5 of these models are shown here because we didn't have data for the other 2 models. And here's the multi-model mean. And same picture. It's basically sea ice concentration increases in the Little Ice Age compared to medieval. So this percentage of area covered by sea ice. So you see in the northern hemisphere, high latitudes, where the normal sea ice edge is, there's just more sea ice in the Little Ice Age than there is in the medieval warm period. In the southern hemisphere, there's a little bit more ice too, although in the GIS model, it tends to want to remove ice, right? So that warm spot in the GIS model in the previous picture was just because the GIS model said, there's no ice there, or less ice there. Could just be due to low frequency ocean variability, but whatever, that's what they did. Okay, so all models show some increase in Arctic sea ice and varied Antarctic sea ice changes. Okay, now here's a comparison of probably the best reconstruction we have of the northern hemisphere air temperature. The blue line is what I showed you before from the climate model, and the black line is what you get from the best reconstruction we can have of the northern hemisphere temperature. And there's an overall agreement in terms of the amount of cooling you get. In fact, it's pretty impressive, right? But there are big differences. For example, each one of these big blue spikes down, which is a volcano, has a less big blue spike in the observations, right? Does everyone see that? Okay. So there could be 3 reasons for that. One is it could be the models are overestimating, that the reconstructions of the aerosol content in the air are perfect, and the models are overestimating the response. It could be that the reconstructions of the aerosol are perfect, and the models are perfect, and the data are underestimating the amount of cooling, which is plausible because a lot of these are trees. When you get back down this far, it's mostly coming from trees. And the third one is the data are good, the models are good, but the volcanic aerosol reconstructions are lousy. Right? So I don't know which one of those answers is right. But overall, the general cooling you get is agrees with observations. It's just the level of spike doesn't. Okay. Here's 4 different reconstructions using sort of improved empirical techniques for reconstructing northern hemisphere air temperature. Unfortunately, this is shown as medieval climate anomaly minus Little Ice Age, so it's the opposite. The medieval climate is warmer, right, than Little Ice Age. And where all the X's are, there's no statistical significance. And it's the same kind of idea that you have overall warming, maybe more in the northern hemisphere, high latitudes than anywhere else, but general warming. Here's a couple of techniques. This is the old technique that you probably want to stay away from, but doesn't show much at all. Okay. This comes from a paper by Wang et al. Really nice paper. Just came out this year. Okay. And there's the multi-model mean, Little Ice Age minus. So again, it's Little Ice Age minus the medieval climate anomaly, so it shows an overall cooling. The general picture is okay, and the amplitude is reasonable. Okay, good? Okay, now it's going to get a little bit hairy for a while, but we'll recover. Okay, so fair agreement. So this is where it gets a little hairy. You just have to trust me. I'm not going to go through the math because there's like 14 slides of math to do this, but it can be boiled down to this. Let's say I have some sort of makeable force. Let's say the sun gets more intense, big sunspots. I know if I start from an equilibrium climate, I know the equilibrium climate means the energy that's coming in and being absorbed has got to be equal to the energy going out to space. Right? If I have a burst of sunlight, everything else being the same, nothing happens yet, I'm going to have more energy being put into the atmosphere, right? So that's the forcing here. I would have a net increase in the amount of radiation coming in. Now, eventually, the climate will warm up, right? And that's the response. And if it warm up to a new equilibrium, the response will exactly cancel the forcing, and the residual will be zero, right? So for a while, I have a forcing, and the climate just starts to warm up, right? Eventually, it'll reach a new equilibrium where the forcing equals the response. The amount of increase in the incoming solar will be balanced by the increase in the outgoing long wave to space. Right? So that's just an energy balance statement. Now, it's customary to say that the response is proportional to the change in the surface temperature. So this is a classic feedback analysis, and we just do it linearly, which actually turns out to be a really good approximation. So you just say that the response of the system is going to be proportional to the surface temperature change, and lambda here is just telling you about the climate sensitivity. Right? It's just a relationship between how much of a temperature response you have to a given forcing in equilibrium. Okay. Okay. So you have it's a new equilibrium. This is zero. The energy imbalance is zero. Forcing by, say, increasing CO2 has got to be balanced by the response of the system, which is to emit more long wave to space. Okay. So now we can write it in terms of the change in the total energy in the system is equal to the sum of all the forcings, volcanoes, CO2, sunspots, and orbital changes. And it's going to be balanced in the equilibrium by the climate response. And lambda here is just the sum of all the feedbacks from the climate system. Okay. So we have lots of feedbacks. We have a surface albedo feedback. That is, let's say the initial forcing melts a lot of ice. Well, that changes the color of the surface and changes the amount of radiation with speed absorbed the surface. That gives you a further temperature effect, right? So there's surface albedo. There's clouds. I can have the clouds change. You know, sun increases and poof, there goes all the clouds, right? Well, that would warm the planet a lot, right? Because clouds presently cool the planet. Right? You have changes in the amount of water vapor. Water vapor is a greenhouse gas. If the amount of forcing changes the temperature, it changes the amount of water vapor in the atmosphere, that's a further feedback in the system. So it turns out there's ways you can actually estimate after the fact what all these feedbacks are and how big they are. So here's an example. Here's a picture of the Arctic sea ice, 1979. I think this is probably an artist's rendition, but given the sea ice extent. If I have 100 units of energy coming in the top of the atmosphere and it's coming down, and it looks down at the Arctic, and I'm measuring the amount of sunlight coming back, I can measure and say how much comes back, and the answer is, over the Arctic today, is 60% comes back. Okay? Now, let's say a forcing results in the change in the sea ice, right? So say something happens, I add extra sunlight, and the sea ice melts, or I increase CO2 and the sea ice melts. Well, sea ice melting is going to change the amount of radiation that's reflected back here, right? Okay, so there's the sea ice melting back, presumably due to increasing CO2, right? That's the party line from IPC, so let's go with it, right? I still have 100 units of sun coming in, right? And then I have reflection at the surface, and I have energy coming back. Here's a teaching moment. 60% came back with sea ice there. How much comes back with no sea ice there? Let's say I'm looking at the same point in space. Here's the sea ice. Here there's no sea ice. How much comes back? Anyone want to hazard a guess? Is it 0? 10? I'll just keep, I can raise your hand as I get your number. 0, 10, 20, 30, 40, 50, 60. Well, it can't be any more. more than it's a darker surface. Okay, it's 45. And the reason is because there's a lot of clouds in the Arctic. And if I take sea ice away, I still see clouds. Right? Turns out that most of the planetary albedo has nothing to do with the surface. It's about clouds. Right? In fact, 88% of the planetary albedo is clouds. If you planted the surface black, not much would change with climate. Certainly if you planted sea ice black, not much would change. Awesome, isn't it? I love this. You find out something really basic you've been explaining to your students for years is wrong. I love it. I could tell you a monsoon story, which is even more horrible, but I won't. Okay. Okay, so what caused the cooling of the ice age? Oh, did I say this? No, yeah. Is it volcanic forcing? Is it solar forcing? Is it changes in land use? Is it changes in greenhouse gas concentration? Or is it witches? So I always said it wasn't solar, it wasn't sunspots, right? But there's orbital parameters as well, right? And what feedbacks are important and how important are they? Is it the ice albedo feedback? Is it the fact that the sea ice age increased in extent? Is it the long wave water vapor feedback? Is it that basically the planet was colder, so there was less water vapor in the atmosphere? Less water vapor means less greenhouse gas, less greenhouse effect, which means cooling, right? Yeah, everyone get that? Long wave cloud feedbacks. If I change my cloud top height, I make my clouds lower, then I lose more radiation space. Why is that? Because clouds are almost perfect emitters of long wave radiation that goes to space, right? So if I have a really high cloud in the tropics, high clouds are really cold, right? They emit very little energy to space because they're so cold. But if I made those clouds shorter, so they were hotter cloud tops, then I would lose more energy to space, right? So there's lots of feedbacks here. There's also cloud shortwave feedback. More clouds scatter more sun. That's a cooling effect, right? So there's lots of feedbacks. I'm not going to go through how you do this, but we can calculate forces and feedbacks using these two methods called APRP for the shortwave and called radiative kernels for the long wave. And I can give you the gory details if you want them, but yeah. So here's the picture again. Here's all of our forcings, volcanoes, greenhouse gases, insulation. We're going to define medieval warm period there and the little ice age there, like we said before. The same two periods we were contrasting the temperatures and the sea ice changes. And we're going to look at what happened. Well, here's a summary plot that says, how did the shortwave being absorbed into the system change? And it goes down, right? So compared in the little ice age, compared to the medieval climate anomaly, shortwave being absorbed in the little ice age, right? Now, that turns out to be balanced by less long wave emitted to space, right? So positive means energy into the system, right? So basically, I get less short wave being absorbed. That will cool. But if I have a colder climate system, I'm radiating less energy to space, right? So that's a warming, right? And these two things almost exactly cancel. This is a change in the energy that's going between the atmosphere and the ocean, and the answer is there's almost no change. So basically, all this change at the top of the atmosphere is saying the atmosphere is readjusted so that there's less energy coming in, but there's less energy going out. And this is just the residual term, which tells you, is the system drifting over a 200-year period? And the answer is no. Okay, so we have a net incoming decrease in the amount of sunlight being absorbed, and we have a compensating decrease in the amount of energy that's being emitted to space. And then, so we have a new balance, but it's a colder balance, right? The climate's colder. Okay. Very little difference in the flux between the atmosphere and the ocean. That's good, okay. Whoa, okay. So here's this breakdown now of the total forcing. We can break it down to like, why was there less energy coming in? And why was there less energy going out? And why is there less energy going out? All has to do with feedback, right? Okay, so turns out this is the change in the flux of energy into the climate system, little ice age minus medieval climate anomaly. And it says the volcanic forcing gives you minus 0.2 or 0.3 watts per meter squared. That is, there's less energy coming into the system because of volcanoes. And it's big compared to the other three. Right? So volcanoes is the answer. Little ice age is cool because of volcanic forcing. Land use changes is the next biggest thing. This is basically converting forests to fields for agriculture. Solar forcing is small, and the greenhouse gas forcing is small. Right? So why the little ice age was cooler than the medieval climate anomaly is because of volcanoes. That's cool. Right? I wouldn't have expected that a priori, but that's the answer. In terms of feedbacks, okay, so let's see, that's the dominant forcing. In terms of feedbacks, these are shortwave feedbacks. These are feedbacks that change the amount of visible radiation that's being absorbed in the time system. And the big one here, big two, one is surface albedo feedback. That is, if I cool the system, I create more snow over land and more sea ice. Those things actually cool the system even more, right? Because they're going to reflect more energy back to space. But another one, which is actually just as big, in fact, probably even bigger if you throw out that model. Each one of these circles is for a different climate model, by the way, is the shortwave water vapor feedback. Now, this is a odd one. Well, it's not odd, but it wouldn't have been on anybody's radar screen up until about a year ago. It turns out that when you cool a planet, you have less water vapor. Water vapor is greenhouse gas, so you have less water vapor trapping energy, so you have more energy being emitted to space. But that's all in the long wave. We've known that since Arrhenius back in 1896. Actually, since Joseph Fourier in 1852. But there's another one that's really important, actually, and that's water vapor is a really good absorber of visible radiation. 20% of the radiation from the sun actually is absorbed by water vapor. This is something that you learn in graduate school as a climate scientist, but then you quickly forget about it. So you're teaching very simple models of climate, and you say, well, let's assume it's all, basically being absorbed at the surface and the clouds are reflecting everything else. But in fact, 20% of it is being absorbed by water vapor. So if I have less water vapor, I have less absorption of sunlight. Right? That's a negative feedback. It means more sunlight gets to the clouds and gets to the surface and is reflected back to space. Right? And it's a pretty big term. It turns out that when you double CO2 in the atmosphere, it is true that if you double CO2 in the atmosphere, you constipate the atmosphere. It's got to heat up to emit more energy, the same amount of energy back to space, right? Yeah, okay, that's the party line for. Well, it turns out that if you look at the energy balance, it turns out that that's only half of the reason why it warms. The other half is because more water vapor absorbs more sunlight, and that's the other half of the answer that no one ever talks about.
Can I just?
Yeah.
So, but that is being absorbed by the atmosphere, but so that just ends up having to be transported upwards with. It's the same amount of energy that it would have had to be transported.
Oh, no, because
although the source term appears in the middle of the atmosphere rather than the bottom, but it's the same source term.
It's okay. So before, if I didn't absorb it, in the atmosphere, I can get more energy to the surface where it's going to reflect, right, and come back. That's how it's going to be. So what you're doing is saying that as long as I have water vapor up there. And especially if I have water vapor and I have low clouds, I'm going to absorb a lot of sunlight before they even see the clouds, right?
Okay.
And so what happens if I remove some of that water vapor and I still have the same clouds, basically I'm going to reflect more energy to space.
So it effectively decreases the albedo, is what you're saying.
Yeah, exactly. Except we don't usually think of water vapor as being about the albedo, but it's really because it's actually absorbing, right? It's absorbing, whereas albedo is referring to just pure reflection.
Yeah.
But in effect, it's what it does. In the sense that it means that there's less solar trapped in the system. But it's because of the differences, because of the feedbacks associated with albedo. Right? Okay. Good. Okay, so those are the two big feedbacks in the short wave. In the long wave, the big feedback is if I have less energy coming in the system, it just cools. And when it cools, sigma t to the fourth tells me I'm radiating less energy, right? So I just lose less energy to space. Okay. Okay. So that's sorry. That's one. That's the Planck feedback. That's the big one. But and it's a negative feedback. If I'm emitting less energy to space, it means I'm not going to cool so much, right? But the other one is the long-wave water vapor feedback. That if I just have less water vapor in the atmosphere, I have less greenhouse effect, so I lose more energy to space, right? So that's a positive feedback. I do something like volcanoes to start the cooling. Cooling means less water vapor because there's just less evaporation going on. Less water vapor means less greenhouse effect. Less greenhouse effect means more radiation going to space. That's a positive feedback. Right? So that's actually the big one. Okay, so how much of the total cooling you get? This is the total cooling for each one of these models, anywhere between about 0.15 degrees and 0.3 degrees or so, 0.29. How much comes from each of these things? Well, the answer is volcanoes is doing a lot of the cooling, about a third of it or so. Long-wave water vapor feedback, just the change in the greenhouse effect, is doing quite a bit of the positive feedback here. And the surface albedo feedback and the shortwave water vapor feedback are also positive feedback. And if you say, well, how much do the total forcings contribute to the cooling? The answer is about half. So about half of the cooling is just due to the direct effect of the forcing. And the other half of it is due to the positive feedbacks. 19% of the cooling is due to the shortwave feedbacks, and 34% of the cooling is due to the long-wave feedbacks. Right? Okay. So let's summarize this, I think, coming up. Oh, yeah. Okay. So that's average across all the models. And here's the answer. Across all the models. Okay. Across all the models. This is the total average forcing minus 0.36. That is 0.36 watts per meter squared, getting less into the climate system due to all the different forcings. 65% of that answer is volcanoes. 13% is land use. 10% is solar, sunspot cycle, and 12% is the decreased CO2. But that's kind of like canceled a little bit by the fact that you have increased nitrous oxide and increased methane, which are kind of working the other way. They're wanting to warm the system. Right? So if we look across all the models, say, like, do all the models have the same breakdown? And here they are. Here's one climate model, CCSM4. This is the French model. We'll come back to that. This is the Australian model. This is one of the GIST models. This is another GIST model. This is the MPI German model.
Max Planck.
Max Planck, yep, thanks. Hadley Center model, British. And you know, roughly they look like the same. Not quite. Oh, I don't know what happened there. That's a 9, I think. Well, it might be a 3. I don't know what it is. There are differences, right? Let me just do this here. Yeah, before we get into this, let me just say one thing here. Okay, so some of them look different. Like these two don't have any red bars in them, right? And because they didn't actually use land forcing, so they're not going to get that cooling, right? The other thing that kind of stands out in the French model here is the volcano forcing is really small compared to all the rest. It turns out that when we figured this out, we couldn't understand this result. And so Alyssa kept communicating back and forth with the people who designed the IPSO model, ran these experiments, and they finally realized that there was a coding problem in their model. And the aerosols were being put in, but within a day, they were basically gone. And they were being replenished. So the aerosol forcing actually turned out to be artificially low in this model compared to all the other ones. So that's kind of a problem. All the results I'm showing you are average on these models, but in fact, we should throw this model out. It's French. Sorry, I love France. The only thing wrong with France is it's full of Frenchmen, right? Just no, someone told me that. I don't believe that at all. Some of my best friends are French. Okay, so it's kind of interesting to say, well, volcano forcing is a really big deal. Here, it's what the main forcing. And yet those two reconstructions were really different looking, right, of volcanic forcing. And the answer is, how sensitive is this answer to which forcing you use? Well, these guys used this one forcing from Gao et al. These four use the forcing from Crowley et al. And, you know, there's differences, but they're not huge, right? So in terms of just the overall cooling, it turns out that it seems to be relatively insensitive. So even though there's big differences in the level of spikes, if you just average over a 200-year period, the amount of forcing you get from the volcanoes on two data sets is very similar. Surprising. It was surprising to me. Actually, and if you compare that model to that model, you find that they use the same data set. But in fact, these guys imposed it as an aerosol in their model. In fact, I think the model actually moved the aerosol around. And these guys said, well, our model doesn't deal with aerosols, so I know how much forcing I should have it reduced by, so I'm just going to change the strength of the sun. So the way they put the forcing in the model is very different. And that actually makes a difference, right? The importance of volcanoes here and here are pretty different. Right? So actually it turned out to be not the two differences in the two volcanic products. It turned out to be how you actually implement the volcanic product in your model matters. And that's still a problem because we're still at pretty primitive days of using aerosols in climate models. Okay, so how sensitive is the answer to what your choice is for little ice age? So here we're going to define little ice age as being 1400 to 1650 instead, and the same thing as the warm period here. And we're going to define a period that's the cooling from 1200 to 1450. Just two different definitions of little ice age. And we're going to look at this forcings and say, here's the picture we just looked at, comparing 1600 to 1850 to the medieval climate anomaly. I'm going to show you two more each for these other two periods, right? Okay, there's that one, and there's the first one. And, you know, basically you get a similar kind of answer. In all three periods, volcanoes are the dominant player, right? In this period here, you have less land use. That's just because people hadn't, you know, started farming at that level of intensity yet, right? What else? In this period, you have very little greenhouse gas concentrations, big contribution of volcanoes. So in each period, you get the same answer. Volcanoes is the dominant reason for cooling, no matter how you define your little ice age. Okay. Okay. Now, so we can answer this question now. What led to the cooling? Volcanic forcing was a third of the cooling. It's just due to the direct effect of forcing. Solar forcing only counts for 4% of the cooling. Changes in greenhouse gas concentrations count for 5%, and land use counts for 7%. I was kind of surprised. Land use comes up as being number 2. Right? A far number 2, but number 2. This is comparing 1600 to 1850 to the medieval climate anomaly period. And then how much is due to the feedbacks? Well, snow and ice albedo feedback turns out to be pretty small, 7% of the total contribution to cooling. By far, the dominant reason for the cooling is volcanoes and the water vapor feedbacks. First, just the greenhouse feedbacks. It's colder, less water vapor, less greenhouse effect. But the other one is less water vapor, less absorption of shortwave. Right? Those are the two biggest. And those feedbacks basically double the amount of warming you would get just from the forcing by themselves. Right? Lapse rate feedback turns out like in a colder climate, clouds, when you cool the climate, you cool the surface more than the atmosphere, which means you're still emitting, you know, more energy to space than you would have thought from the surface temperature. And the long wave cloud feedback means that in a colder world, clouds on average are shorter, which means the top temperatures are warmer, which means you're emitting more energy to space, and that's a cooling effect, right? Okay. Okay, so that's half of the cooling is from the forcing itself, and half of the cooling is from the feedbacks. The way the climate system is responding to those forcings. Okay, turns out the total feedback is pretty similar to what happens if you did a 4 times CO2 experiment. You took modern day climate and just increased CO2 by a factor of 4, and you do the same analysis. The feedback is about the same strength. Okay. Right. Okay. Good. So what causes the model spread? So why is there this spread in the model response? Well, it turns out quite a bit of it is due to uncertainty in the forcing. It varies from minus 0.16 to 0.32. That's a 100% difference between the different models. Mostly due to the differences in the way aerosols are treated within a model and not due to the differences in the products. Okay, so that's surprising. There's also good news because these reconstructions of volcanic aerosols it's hard to do, right? I mean, there's a lot of uncertainty in them. Okay. There's uncertainty in the feedbacks. Feedbacks vary from 1 watt per meter squared per Kelvin to 2, which is similar to the range you get when you increase CO2 in these models. It's mostly due to the fact that we don't know how the clouds will affect the shortwave radiation. This is the big Achilles heel in the projections of what's going to happen in the next 100 years in climate. How will the clouds change? How will the albedo of clouds change? That's the biggest uncertainty. The other uncertainty, which is not small in this case, is the lapse rate feedback. That is the temperature structure within the atmosphere, how that changes. Turns out to be sensitive to how much sea and ice changes, in snow changes. Okay, so the last point I want to make here, okay, we're doing good, is where does the memory come from? So if it really is these sporadic volcanoes that are burping, every once in a while, and they last, I have an emissions of massive aerosols. Aerosols stay in the stratosphere for about 2 years, and then they fall out, completely gone to a volcanic eruption. How is it that we have this 200-year period that's colder? Right? How does that happen? Where's the memory, that's connecting these individual volcanic events? Here's the volcanic record, right? It's very spiky. And here's one model's simulation of what happened to the sea ice. And you can see the sea ice bounces up and down. There's natural variability here. Maybe some indication here when there's a big volcano, it went up, right? But there's other ones, big volcanoes, where it didn't go up. So it's just natural variability. But there's an overall trend here. Can you see the trend? There's an increasing trend. So there's more sea ice at the end of this simulation than there is at the beginning. So where's this memory coming from? Not in the aerosols. Aerosols drop out of the stratosphere really quick, a couple of years. Okay? So the albedo creeps up slowly over the last millennium, but the cooling is primarily due to episodic volcanoes and water vapor feedback, right? Remember, the albedo actually is a really small player in why the temperature cools in all of these models. Albedo changes. So you can think of a bunch of ways you'd have feedbacks here, longer-term feedbacks. One would be changes in the Arctic sea ice thickness. The problem with this one is if you watch Arctic sea ice is created in the Arctic, it's blown around by the winds, and it exits out Fram Strait into the North Atlantic in about a 6-year period. That's kind of too short to have memory, right? Every 6 years, you clean the slate, you start again. The other problem with this is that cooling is mainly due to the direct forcing and water vapor feedbacks and not albedo. So who cares, right? Albedo, sea ice is increasing, but it's not a cause for the ice age here. It's a response, right? Okay. So albedo accounts for only 7% of the total cooling. So it's not in sea ice changes. That's not amplifying. That's not what's amplifying and giving you memory of 200 years of cold conditions. That's not it. You could say it changes in ocean overturning circulation in the Atlantic. The problem with this is it's a very strongly dependent on the model. You get very different answers across different models, and yet the models all give you cooling. So that kind of suggests it's not this. And the other thing is that the changes in heat transport, ocean heat transport into the North Atlantic in these models are basically zero, really small, right? And so you can't say, well, yeah, the ocean circulation slowed down, delivering less heat to North Atlantic, and so it's cooling, because that's not what the models are doing, yet they're still giving you the observed cooling. You could say the ringing of volcanically induced changes in ENSO and its impact on global climate via atmospheric teleconnections. This is a stretch. The main problem is that changes are limited to a few years to a few decades at the most. They're not going to get you out to 200 years. Thermal inertia of the next layer. So if I just have like a burst of wind and more evaporation, I'm going to cool the ocean surface, right? And then next year maybe I have weaker winds, I'm going to warm a little bit. But basically what the ocean is doing there is just integrating up what the atmosphere is doing. In this case, it's integrating up what the volcanoes are doing. Right? So a big volcano goes off and says, whoa, a lot less radiation, I'm going to start cooling. Right? But then next year, no volcano, so I'm going to start going back to normal. It takes me time to get back to normal. If my mixed layer is really shallow, it takes me no time. If it's very deep, it takes me a lot of time, right? Because I just have a lot of heat capacity change. Okay? Believe it or not, this explains a lot of the climate variability we see in the last 100 years as well. It's just the ocean, the upper ocean, just integrating random variations in the atmospheric weather. Okay, so the memory depends on the depth of the mixed layer and whether sea ice is present or not. Because if you put sea ice over this, all of a sudden you don't have any heat capacity, right? You can't access this really nice mass of water that's going to store or release energy, right? Okay? It turns out the time scale of getting rid of a temperature anomaly in the upper ocean is 3 months if you have a 50 mixed layer. It's 2 years at 200 meters, and it's decades if you get a deep or seasonally mixed layer. Okay? So I was really curious about this, so I just actually coded up. I was bored in the back of a really bad seminar one day and just coded up this single one-dimensional model of the world's climate system, which is just basically an atmosphere, a one-layer atmosphere, hooked to a slab ocean, hooked to a deeper diffusive ocean, right? So when the slab got colder, it would slowly diffuse energy, less cold water down below, vice versa. And I just put in numbers I thought were reasonable. I just gave it the volcanic forcing and got this red line. First time. I didn't even tweak the parameters, right? And the blue line is the temperature change you get from the GCM, from the climate model. Not bad, right? Right? And actually, this isn't surprising. It's not going to be, well, you certainly don't want to hang your whole answer for why there's a little ice age on a one-column model. But the fact that you have GCMs and you can reproduce it with something so simple means that basically the essence of what's going on is really quite simple, right? You just have stochastic volcanic forcing. It's greater over a 200-year period of the little ice age than it is during the medieval climate anomaly, and the ocean is just integrating those anomalies up. That's all that's going on. Right? Okay. I like it. If you're someone who took literally 6 months to make that run with a climate model, you're probably not too happy. But I mean, you should be, because it's like just understanding what goes on in a really complex model, right? I don't know how they feel about this, but I should just wipe out the name of the model so no modeling group gets offended, or they all do. One or the other. So conclusions. Models show global cooling from 1250 to all the way to 1850 compared to the medieval climate anomaly, which is coincident with this period called the Little Ice Age. About 2 degrees, 0.2 degrees cooling northern hemisphere average, annual average, roughly agrees with the proxy data. The cooling is half due to forcing, volcanic forcing, half due to feedbacks. There's a list of all the forcings. There's a list of all the feedbacks again, mostly water vapor feedbacks. There's a large model spread in the cooling due to uncertainty in both the forcing and in the feedbacks. In the feedbacks, the ones that are most uncertain are the lap straight feedback, the temperature structure, the vertical temperature structure in the atmosphere, and the shortwave cloud feedbacks. Okay. Net climate feedback is 1.85 if you're into this watts per meter squared per degree C. It just tells you effectively for a given forcing, right? If you just had no changes in the climate system, basically it just tells you that the actual response you get is twice as big because of the way the climate system starts rearranging things like clouds and temperature and things, okay, and water vapor. That's similar to what you get in 4 times CO2. The net water vapor and last rate, oh, this is a nerdy thing, okay. Mixed layer memory may be sufficient to explain what's going on. Right? You don't require changes in ocean circulation, changes in sea ice or anything. Okay, so that they're not. We didn't do that part. And then, so the last point here is there's an effort, I think, or there's also maybe an excuse for, like, say, reconstructing past climates with the idea that you're going to help constrain what the amplitude of the climate feedback is. And that's going to be useful for understanding how climate will change in the future. That's complete nonsense. Right? The feedbacks, as I showed you there, are really complicated, and they depend on the forcing, type of forcing. And we've known this for quite a while. The value in doing this reconstruction of the past climate isn't to constrain the feedback sensitivity, the sensitivity of the climate system. It's to understand if your climate model actually getting at the processes that are giving you this different climate. Right? That's what it's important for. And whether or not the LGM climate sensitivity is any different than what we expect in the future is irrelevant. It's more like, are you getting the LGM right? Are you consistent with the proxy data? And if so, what is the mix of processes that gave you that cooling? Right? Same thing with the middle hull thing. Are you getting the climate right, and are you getting it right for the right reasons? Right? So the total climate sensitivity is not a very interesting number, not a very useful number, despite 100 pages of the last IPCC devoted to it. It's just not appropriate to think of it like that. Okay? So that's just a personal pet peeve I have. The same thing comes up when you think about geoengineering. You can't think about, say, dumping a lot of stratospheric airflow and just canceling the effect of increasing CO2 because the structure of the forcing is different, and therefore the feedbacks are different. And the total, you might be able to adjust the total temperature to be the same, but the pattern of the climate response is going to be entirely different. Okay, well, that's what I have. Sorry. Okay, go ahead.
I have a question about land use. I'm a big fan of Bill Ruderman and, and what's his name in Switzerland?
Yep. Jed Kaplan.
Yeah, Jed.
Yeah.
We talk a lot about the pandemic and major wars that happened during that period.
Yeah. Yeah, I think, that paper, I don't know if you were in the room when I showed that Witches paper, but I mean, the idea is that there's a lot of climate, there's a lot of climate change and a lot of extremes in climate there. And, if you're a society that's on the edge already, it tends to not be a good thing, right?
But it's the feedback.
Oh, so what's in this particular model? What's prescribed is the history of the land use that's reproduced from people like Jed. It wasn't. I don't think it was Jed, but it's like that. So there's not an interaction here. It's not like the climate is changing and the model says, okay, I can't have a spruce tree anymore, so I'm going to put a flower or something, right? That's not what's going on. The model's actually told this was the land use history, right, in time. Right, so that's in there. And for that last period, it's the second most important source of cooling, right? Exactly. From the change in forest to ag. So it's going from 1200 AD to this period of 1600 to 1850, where a lot of the increase in ag stuff was due to more land in use for ag, right?
Right, so that's probably feedback.
And CO2 does go down, but CO2, the amount of it goes down here doesn't do anything to the climate. Right? So that would be inconsistent with CO2 as being a feedback in a climate sense, because these changes are too small to show up. Like the land use change itself just gives you enough cooling to do it. Yep.
Regarding the volcanic forcing, I'm curious about the difference between one there's a couple of large events,
yep,
and whether in modeling you can model what the difference would be between singular large events to drive this forcing versus, a number of smaller scale volcanic events.
Yep.
I'm curious about the degree of forcing back to like cumulative, back to your flat layer ocean. Is maybe it's insensitive, but is it, you show there that like, do you need like that first period of a large event followed by a couple of subsequent big events to sort of start the system cooling, and then after that it isn't so important.
Yep. So
after that's here. That was even there.
So we think if the ocean is just integrating up what's going on, all I really care about is the net aerosol loading over certain areas.
So it doesn't matter about the...
So that's why these two agree. If you calculate the net aerosol loading over this period here in one data set and the other data set, they're within 10% of the same answer, which is a miracle, right?
No,
I mean, no, it's not a miracle.
What I'm wondering about is to get your cooling going, though.
Oh, yeah.
Right, that you've got to have...
Right.
It's the one before maybe.
But you don't need a spike. You don't need a spike to get it going. I could take this away and take it and distribute it over a lot of small spikes here and get the same amount of cooling. There's not a lot of difference in whether it's a spike or not. I mean, there is a little bit. It depends on, it's more sensitive to how much that original spike, how deep of the ocean it cools. If it cools, right, so that matters.
Right.
And like I said, I just happened to pick some parameters and they worked, so I stopped. I didn't try to, I mean, I know you can actually write equations down of how sensitive the answer is, quantitatively, how sensitive the answer depends on the frequency dependence of the eruptions, but, it's kind of beyond the point.
Well, and on the same line of thinking, what about the geographic position, either being large tropical, large northern hemisphere, and the sulfate load?
Right. So the reason why, when I said it was a miracle, it's not actually a miracle because these guys are using ice cores, and they're basically looking at aerosol concentrations, and they're trying to map it to total aerosol loading. So they might disagree on when it goes off. They might disagree on the intensity, because maybe one guy used the core, one team used the core, where that distribution was not centered in the same year, or was more spread out in that core because of whatever, melting or, I don't know, snow blowing. But it turns out as long as you have roughly the same total loading over this period of time, you get the same answer. And it makes sense that they're not far off, right? In terms of latitude dependence and time dependence, remember those plots I showed you where there's 1 here and 4 here? Each one of those models put it in a different latitude distribution, right? So it seems to be a little bit less sensitive to that. Right? Yeah.
Maybe one last question.
That's
I guess
cool.
it'll be
Just
Mark.
as a contrast, if you make that go forward, what's that 1850 to now look like on the same scale as the forcing?
I could do it. I didn't do it.
I'm just curious, does it go back down to zero, back to what you're saying, you don't really need anything? Do you get flatline, or if it isn't flatline, what's going on?
Isn't the 20th century less volcanic activity than before? I mean, I can't remember the answer, but that would be a good one to do. The other one would be really interesting to do is, the land use becomes more and more important as you go to here. Well, it turns out land use between 1850 and 1960 was unbelievable, right? So actually, it'd be interesting to see how much cooling so we've had warming, really large warming over the 20th century. But this would argue actually there's a really large cooling that's happened because of land use. It's in there somewhere. And presumably someone's done this calculation independently and said, let's just do the land use alone over the 20th century and see how much cooling we get, because a lot of that 0.85 degrees C warming we see over the 20th century has to be due to some contribution of cooling, which is not trivial due to land use change.
Well,
Up to 1960.
Volcanics were slow through the 40s.
Right.
Basically, post-60s, you get a re-uptick.
Okay, good. And you also see it cooling, right?
Yeah.
60s?
Yeah.
Yeah. So it'd be, I mean, I assume that the IPCC guys did this, but in fact, I just wrote an email to Alyssa last night, like 2 in the morning, thinking someone should actually check, if they haven't already, what the land use cooling is over the 20th century. Because not only should it cool a lot, but it stops in 1960. When the Green Revolution came in, people stopped clearing land, and they started intensifying agriculture, right? So land clearing hit a maximum in 1960. It's been relatively slow since then, right? I mean, we are still clearing land, especially the Amazon, right? But it's actually nothing compared to 1850 to 1960. Thank John Deere for that.
And through the 60s and 70s, though, you had a huge uptick in reflective surface aerosols, too, from
coal. Yeah, so it's like the 20th century is it's tough to sort things out. I mean, the warming has to be increased CO2, right? But how much of that warming is, I think it's still an open question. And it probably will be until 2100 when we hit 4 degrees C. It'll be obvious how much you get when you increase CO2.
David, thanks.
Thanks.